Hello and welcome everyone once again to another edition of a Fronius webinar. These webinars are organized and presented to you to provide you information about Fronius products and solutions. And today we shall be discussing the benefits of HV lithium-ion batteries. HV, of course, standing for high voltage. Yes, it's true that battery storage is a very hot topic of discussion, especially in the sub-Saharan Africa region, because of the relatively insufficient or sometimes lack of grid supply. So we have decided to present this webinar to give us or provide us information about the benefits of lithium-ion, or basically lithium-based batteries storage solutions. And to do this with me today is Byron Kotze. Byron is the technical sales advisor for the Southern Africa region, while myself, Cyprian Okolo, the technical sales advisor for the Western Africa region. Byron is based in Johannesburg, South Africa, while I am based in Lagos, Nigeria. So let's have a brief look at the agenda we have for you today. So first up, we shall be discussing battery storage chemistries. We shall be taking a brief look at the architecture and chemistry of a cell. We shall have an overview of lithium-ion chemistries and the durability. And then Byron will come in at this stage to continue from lifespan and second life applications. Differential characteristics will be provided to you. And then answer the question why going for, or the preference for lithium-iron phosphate battery chemistry. And then we'll now provide you with information about the BYD battery box HVS and HVM, which we normally partner with in terms of implementation of the Gen 24 storage solution. And then, of course, also give us some instances of LVL battery installations. Good. So let's now start. But before we do so, please feel free to ask your questions with regards to this topic during the webinar by using the chat function that you would find at the right-hand pane of your display screen. And we shall endeavor to answer your questions during the webinar. In a case where, due to time constraint, we're not able to do so, we shall, of course, reach out to you via email and provide you with the answers to your inquiries. Your opinion is very, very important to us, so please give us feedback about the content that we provide to you in our webinars. Thank you. So let's now start off with battery storage chemistries. Yes, of course, we know there's so many battery setups or constituents or chemistry available out there. Here we kind of listed a few of them and gave you kind of instances of how they look like, including the hybrid ion battery. We have the sodium sulfate, sodium nickel chloride. We have the nickel cadmium, which is a bit popular, I would say, because with this, there's flexibility of you having it in having the electrolytes in an acid or an alkali format. We have the redox flow battery. We have the zinc bromide. And then we have the very popular lead acid and the lithium, now popular also the lithium ion battery chemistry. So these are quite a handful, but then for comparison's sake, we have decided to take just two of these battery chemistries and then do a basic comparison between them. So these are the lead acid and the lithium ion batteries. So taking a look at the lead acid batteries, in terms of the positives, it's robust and reliable. In terms of investment costs, it doesn't cost that much. But then it is weighty in terms of negative feedback per se. It's weighty. It's susceptible to outgassing. There's distance of forced air circulation. It has low cycle stability, low lifespan, and then um, um, you have to perform some maintenance practices on them, especially as it has to do with saturation charging. And then for the lithium-ion battery, it comes with a lot of positives because of its high cycle stability, no memory effect. It's lesser in weight. It's very safe. It has a long lifespan, high system efficiency factor, high voltage as one of its characteristics. Involves no maintenance. It has also high energy density, but then it comes at a cost, of course. In terms of a negative feedback, one would say for now is a high investment cost because it costs much more than the lead acid battery. But then with the advancement of technology, this is being addressed, I would say, because as time goes on, the cost has actually experienced a continuous decrease. So let's now have a look at the architecture and the chemistry of a battery cell. Well, let's start off with the saying that all batteries are not equal. So you can say, okay, the composition of one battery is the same thing as the composition of others, as I've earlier shown you, because there are three main characteristics or three main um, attributes that affect the final characteristic of a battery. So we're talking about the cell chemistry, the cell architecture, and then the battery management system. Cell chemistry, with regards to the active material of the particular battery cell, it could be a nickel cadmium or lithium iron phosphate. In terms of architecture, what is the structure of the cell design? That's uh, this particular attribute. So it could be a cylindrical cell or a pouch cell. For battery management system, this has to do with the control of the system down to the cell level. Control in terms of determining the charging and discharging process. So all these attributes combines to give us the general characteristic of a battery system. So this now goes ahead to tell us information or give us information about the useful lifetime, the cycle stability, the calendar aging, and then the C rate. Okay. So for the cell architecture, this is just to put it in perspective. We have different kind of cell architecture. We have the cylindrical cell, as is found in Fronius solar battery. This kind of cell has a capacity of 3 ampere hour. And then we have a pouch cell, which is found in the LG Chem Resu, which has a capacity of 36 ampere hour. And then we now have the prismatic cell, which is what the BYD battery box is composed of. And then this has a capacity of 60 ampere hour. So by cell, we of course mean the smallest unit of the battery system. Okay, so going forward, with reference to the prismatic cell that is found in the BYD battery, we can now see that these cells are now seriesed. And then this series now forms the composition of what we have in the module. So in this case, we have 16 cells that are seriesed. And then this would now give us, by the time we obtain the cell voltage. So for this particular system, which is made up of lithium iron phosphate, the cell voltage is 3.2. So if you series 16 3.2 battery cells, prismatic cells, we're going to get 51.2 volts. So that gives you the module voltage. So meaning that If you check the voltage across the positive and negative terminal of this particular module, you're going to obtain 51.2 volts. Now, the cell capacity is 25 ampere hour, but because they are series, the cell capacity remains 25 ampere hour. If they were in parallel, then the cell capacity will be reversed, and then of course the voltage will also be reversed because it will now be 3.2. But in this case, since they're in series, in terms of ampere hour, the ampere hour rating remains the same, which is 25 ampere hour. So therefore, to obtain the usable capacity, you now multiply the cell capacity, which is 25 ampere hour, by the module voltage, which is 51.2 volts. So that gives you a total of 1.28 kilowatt hour per module. So, and then now that you have the capacity in kilowatt hour per module, you would now have to stack these modules up to about 4 or 8, depending on your load or backup requirement, to give you what is needed in total. And then, of course, you have a battery management system that usually comes with the system to, of course, manage the battery charging, discharging, and then overcharging and over-discharging protection also. Okay, so going forward, let's now have an overview of lithium-ion chemistries. Yeah, so basically we have lots of a catalog of requirements that are expected for batteries to have. Of course, top of the list would definitely be the costs, because one would have to look at the purchasing power, and then we'll now talk about safety with the respective certifications, lifespan, energy density, power density, discharge characteristics, or depth of discharge, if you want to call it that way, self-discharging, operating temperature, and then overcharge and over-discharge protection. So having all these requirements that are expected of a battery system, you might want to find yourself at crossroads, because at the end of the day, you would have to make some trade-offs per se. Do you lean towards safety, energy density, costs, or power density? Okay, so let's have a look at the next slide to help us make this decision. You now might want to ask yourself the question, which lithium-ion chemistry is best for our application, or for the application you want to implement the batteries for? So in order to help us or to guide us make this decision, I have a hexagonal structure of choice or characteristics to help us make this decision. So first off, we're looking at specific power, we're looking at safety, performance, lifespan, cost, and then specific energy. So in every case, we'll need to make a decision that would help in getting the best possible characteristics out of all these features as listed. Because at the end of the day, we can't really have it all, because yeah, that's just basically it. We would now have to make a choice and then lean towards specific features that will satisfy the application that we want to implement the batteries for. So having said so, let's now look at this comparison criteria as mentioned in the previous slide. This time around, making a reference to specific battery chemistries. So let's have a look at this one here, which is lithium cobalt oxide. As you can see in this case, it performs excellently in terms of specific energy, but has a very low performance in terms of lifespan and safety. Taking a look at the lithium iron phosphate, it has excellent performance in terms of lifespan, safety, and has a relatively good rating in terms of cost. Specific energy is a bit low, but specific power and performance are also on the good side. So you have other cell chemistries, as you can see. So these performance rating now helps the installer or the engineer to make the decision on which battery chemistry to make use of or implement. But just as I've earlier cited, the lithium iron phosphate, we can also see that the lithium nickel manganese cobalt oxide, quite a long name, has also a very good performance coefficient in terms of lifespan, safety, specific energy cost, specific power, and of course, general performance. Good. So for today's best lithium-ion chemistries, it's best to go for what gives you safety, stability, which in this case for the anode material is graphite. And then in terms of the cathode material, we'll also stick with what gives us the best of safety and stability, which in this case is the lithium iron phosphate and then the lithium nickel manganese cobalt oxide. Good. In terms of durability of lithium ion chemistries, we definitely have to talk about the aging of this kind of battery. When we talk about aging, we're actually referring to calendar aging and then cycle aging. So simply put, calendar aging is basically aging due to non-usage, while cycle aging is basically aging due to usage, simply put. So we're going to have a brief detailed look at them. So in terms of calendar aging, we have lots of factors that are responsible for this. So it has a very strong dependency on temperature, voltage level or SOC, and then of course the Arrhenius law, which states that there is a degree of decrement in lifespan for every 10 degrees increase in temperature. And then we have the lithium-ion chemistries itself tending to disintegrate while during the shelf life. And then we also have, just to give you operating strategies that are best to implement, which includes avoiding high temperatures over a long time span. Best operating temperature in this case is usually between 20 to 40 degrees Celsius. And we should also try to avoid long idle times of fully charged batteries. This would, of course, help in this to prevent or reduce calendar aging. So how about cycle aging? Like I said, cycle aging is, of course, aging due to the continual usage of the battery. But then the truth about the whole thing is wear out, because all good things definitely come to an end. So like I said, this is aging due to usage. This could be also attributed to the temperature, because as the usage continues, the temperature, there's of course an increase in the temperature coefficient. We also have both the effect of voltage level or state of charge, cycle and current intensity. This could also be as a result of mechanical stress, mainly on the cathode side, due to formations of crack and then disappearing of electrical contact as time goes on or as the usage continues. And then, of course, the split up of electrical contact as the usage continues also. So we can effectively say that total aging is equal to the summation of the calendar aging and cycle aging. And then just to put this in perspective, there's just an example here with the information about a particular product, battery, which has the calendar lifespan to be 10 years and then the cycle lifespan to be 2,500 cycles. So the question here is, how long can the battery be used in the most efficient manner, with the assumption that 250 cycles, assumption of 250 cycles per year. So straight off answer for this is it will experience or have end of life after 5 years with 80% of the initial capacity. Okay, so basically these are usually standard, especially for batteries implemented for electric vehicles. Okay, so the explanation for this is that in terms of calendar aging, after 5 years, the battery will depreciate to about 90% of the initial capacity, which is a negation of 10%. And then for cycle aging, 5 years would equal to about to 1,250 charge cycles. So this leads to an additional loss of 10% capacity. Okay, so which now gives us a total of 80% of the initial capacity. Good. With regards to the previous slides as mentioned, we would now want to inform us about what we call blocked cell capacity. Because for batteries, generally speaking, for large capacity batteries, with reference to specific energy density, it is required that some part of the batteries are blocked. These are what we call the non-usable part of the battery. That is why, in most cases, when we look at the battery nameplates, we see what is called usable capacity. So you could have a battery that is, say, 27 kilowatt hour, for example, but then they will now tell you that the usable capacity is 20 kilowatt hour. So this automatically means that some specific capacity of the battery has been blocked off, and then this is done so as to elongate the lifespan of the battery. So having said so, we have what we call the nominal capacity, which is called the gross capacity. That is the total capacity of the battery as manufactured. And then we now have the usable capacity or the net capacity, which is what is available for usage. Okay, so various battery cells have this implemented, while some don't because of its characteristic performance level. So it can accommodate a total drainage or discharge and then full discharge of a battery. So this is what we see basically in cell phones, for example, because you can actually discharge cell phones down to 0%, and then of course charge it back to 100%. So specifically speaking, when comparing the depth of discharge, because this obviously gives us an information about the depth of discharge. So basically, depth of discharge is the allowable depth to which the battery is discharged. So for smartphone batteries, as you can see, depth of discharge is usually up to about 80%, while for stationary PV battery systems, we tend to find depth of discharge of about 80, sometimes to 90%. So basically speaking, for smartphones, we can have it, fully charged and then have it fully discharged, as you can see or as illustrated. And then for stationary PV battery system, would have the blocked out capacity protected, and then you only have this usable capacity to make use of. Good. So let's now talk about battery C rate. Well, the C rate of a battery is basically the measurement of how a battery can be charged or discharged, basically speaking. So for a battery of an instance of 10 kilowatt hour, if a battery has 1 C rating, then with the charging power of 10 kilowatts, then the time for charging of this battery is given as 1 hour. And then if it is 2C, then the charging power increases. And obviously, if the charging power increases, it means that the time for charging will definitely reduce. And then conversely, if the C rate is halved, then the charging power is 5 kilowatts. And then, of course, it will take longer time to charge the battery, as you can see. So basically speaking, the bigger the battery implies higher charging and discharging power. So for thermal management, it is advised to keep the battery at within the prescribed temperature range, which is between 20 to 40 degrees. Anything below or above this would, of course, affect the lifespan. That is either, of course, reducing the lifespan, reducing the performance, and then, of course, leading to thermal runaway in terms of high temperature cases. So, summarily speaking, you tend to find that batteries that have that can achieve state of charge of 100% used to have usually have smaller number of cycles, as you can see, whilst those that have lower SOCs, like 80 to 90%, they usually have higher number of cycles, as is noticed for stationary batteries and those implemented for EVs. So with that, I have come to the end of my part of the presentation. Byron will be stepping in now to continue with the rest of the presentation. Byron?
Thanks, Cyprian. So next we're going to be talking about the lifespan and second life applications. So what are the influencing factors to the lifetime? So this is referenced as the battery aging. So there's two differences. There's cycle stability as well as calendar aging that can influence the battery's aging itself. So with aging by usage or the cycle stability, this is dependent on the cell's chemistry. So if it is a lithium-ion phosphate, for example, if it's a lead-based battery itself. Another influencing factor is the DOD, or depth of discharge. So the amount of which the battery is discharged and then recharged, for example. Another influencing factor is the particle cycles increases the lifetime over proportionally. Another thing is the charging rate. So this is the charging / discharging rate power of the battery itself, as well as what Cyprian has just touched on is of the operating temperatures. So obviously if the battery is at a much higher temperature, this will have an influence on the cycle stability. And also if the battery is too cold, it also plays a factor into the cycle stability. Next is the calendar aging. So this is the aging by time. So this will also be dependent on the cell's chemistry itself. So whether again it is a lithium ion phosphate battery, for example, or a nickel-based battery. Again, also mentioning about the ambient temperatures at which the battery is maintained at, as well as the increase of temperature decreases the lifetime of the battery itself. The durability of batteries. So this is a long-term experiences given new insights. So manufacturers give long guarantees. So anything from 5 to 10 years. So this equates to 100,000 kilometers up to 240,000 kilometers, with a 70 or 80% capacity remaining from that battery cells. So for example, the VW e-Golf, you have an 8-year guarantee or 160,000 kilometers equivalent to allow up to 70% capacity still remaining on that battery's life cycle. As well as for the BMW i3, for example, also an 8-year or 160,000, also giving you a 70% capacity remaining of the battery itself. So what is the second life scenario for batteries? So obviously on the life cycle of the battery itself, its first life is alternatively utilized for the automotive industry. The second life is a stationary application. So this is where your PV installation will then become as the second life cycle of the battery itself. And this is due to the remaining capacity of 60 to 80% is still usable from the first life that was left over. With second life applications, so it's primarily used for grid stabilization or for backup power itself. So for example, with grid stabilization, is used for our example is the Amsterdam Arena. So this helps with stabilizing the available grid at the moment. So it's not to do with a grid outage, but just to help stabilize the active grid at the moment. So if they do notice a high shift in power availability, they can use these batteries in order to create a stabilization for the grid itself. For backup, this is obviously referring to if there is a sudden loss of full grid capacity, you will then rely on the batteries to then allow for the batteries to help sustain your utilization of power. So the recycling process, so this will happen after the second life of the battery has been sustained. So there will always be valuable resources in the battery itself, and this gives you a cycling rate of up to 70%. So there's aluminium and copper are the active materials, for example, that are inside the batteries itself. Energy generation with usage of remaining charge. For example, in Bremen, in Germany, they have a capacity of 10,000 tons per year that is recycled from batteries itself. So what are the differential characteristics? So the depth of discharge. So typically for gel or lead acid based batteries, you have a low depth of discharge range, so usually around 50%, whereas with lithium ion batteries, you have a relatively high depth of discharge values, so usually up to 80%, if not more, depending on the brand and the utilization of the battery itself. The energy density, so this is talking about how the available kilowatt hours per liter equivalent is available. So for gel lead based acid batteries, it's 50 to 90, whereas for lithium ion batteries, it's 125 to 600. So this is why we're referring to lithium ion batteries having a much greater, less weight, Again, this is referring to gel or lead acid batteries taking up to 10 hours and above to fully recharge, whereas lithium ion batteries can take anything up to 3 to as low as a few hours in order to recharge fully. On your warranty periods, normally gel or lead acid batteries usually obtain a warranty of up to from 3 to 4 years, whereas lithiums can range from up to 9 to 10 years. So even though the lithium ion batteries are more costly in a sense, you are getting a much greater product in a sense of a warranty period that is available for it. So under the lifespan or second life application for gel or lead acid batteries, so this will be sparingly depending on the applicable within very short periods, or with lithium ion based batteries, this is usually applicable over longer periods. So it will take much longer to decrease the lifespan of a lithium ion battery, whereas compared to a gel or lead acid based batteries. So why would you utilize high voltage lithium iron phosphate batteries? So this is due to the ease of installation. So the modules are easily stacked to achieve the required or optimal voltages. Minimal installation effort. So this process can be done by a maximum of 2 technicians, for example, or less, depending on the size of the application. Safety. So all active components are embedded in a secure enclosure, which is IP rated of 55 for it. The BMS or battery management system ensures proper battery operation, so charging and discharging, and this allows for an optimal service life. Whereas most other battery technologies, for example, the lead acid, rely on external SOCs or state of charge or LVD managements for it. With lithium iron phosphate batteries, you also get a highest efficiency. So this with your power conversion of a round trip compared to a PV battery load. Low voltage battery systems. So this is using transformer based hybrid inverters, whereas high voltage battery systems are mostly coupled to more efficient transformerless PV inverters. So this is again mentioning about the overall system efficiency. So with higher efficiency equals less expense grid power consumption. So especially for self-consumption systems, it'll make sense to use a lithium-based battery. So this will ensure much better energy independence, as well as much better return on investment figures when comparatively with lead acid batteries. When mentioning about the overall system efficiency, so low voltage round trip efficiency is about 94%, whereas higher voltage round trip efficiency is 97%. So if you're considering a 10 kilowatt peak PV installation, your daily energy is 60 kilowatt hours. This will give you a low voltage battery combo of 56.4 kilowatt hours available, whereas on the high voltage battery combo, this will give you an efficiency of 58.2 kilowatt hours available. So this gives you a daily difference of 1.8 kilowatt hours in difference. So over 1 year, this equates to 477 kilowatt hours in difference. So the overall system life is then 11,925 kilowatt hours. So this is where you will then consider the cost of the energy, and then your own supply is when you have an overall system service life. So next we'll be talking about the BYD lithium iron phosphate high voltage. So this is the HVS and HVM batteries. So with BYD's LVL series, so this is the low voltage battery systems, so 51.2 volt DC. It allows you to be scalable from 11.4 kilowatt hours to 983 kilowatt hours in total. So this is up to 64 modules connected in parallel. They are cobalt-free lithium iron phosphate batteries, or LFP. So maximum safety and also life cycle and power. Also allows space saving via the ability to stack 2 premium batteries, and also add additional batteries in parallel to expand the system later on in future. With BYD's HVS series, so this is the high voltage battery systems. So this is scalable from 5.1 kilowatt hours or 2 modules up to 38.4 kilowatt hours available. Again, these are cobalt-free lithium iron phosphate batteries, or LFPs, and they're also capable of high-powered emergency backup and off-grid functionality. They've got a patent internal plug design requiring no additional wiring. So they're simply modules that stack on top of each other to allow for an integrated battery backup. So here we have some compatible inverters and brands that utilize the LVS or LVL series. So this is a typical microgrid application where it's utilizing the Fronius inverter. So it's a transformerless inverter, and then obviously the Victron, which is a transformer-based inverter. So that is why it's recommended with the Victron using the LVL, as it is a transformer-based inverter. So here, for example, is a typical 3-phase installation. We've got 3 Victron Quattro 15s, for example, and you've got a single Fronius snap inverter to act as the AC coupled in the system, and then followed by your LVL battery system. With the Fronius or Gen 24 and the BYD HVS, so this is the combo for a Fronius Gen 24 plus SIMO, AC coupled with a Fronius SIMO snap inverter connected to an HVS battery. So here's the Fronius hybrid inverter that's utilizing the BYD HVS battery, and the Fronius snap inverter is AC coupled to help cover daytime loads without utilizing the battery entirely. For further information, it is available on our website itself under business unit, followed by solar energy. You will then use installers and partners, followed by products and solutions, and then also technical data is available, as well as our info center, service and support, downloads for any manuals or any how-to videos is available, as well as contact details for relevant applications. So if it's whether it's regarding trainings to after sales support, you will find all details under the contact information. So on our homepage itself, you can then download instructional manuals itself. And on our YouTube channel, we've got our how-to installation videos, as well as webinar recordings and a dedicated Sub-Saharan Africa playlist. For your Fronius team, so for any technical questions, trainings, sales international and after sales service, as well as you can contact our TSAs directly. So for the Western African region, you can contact Sabrina Kulu, myself, Byron Christopher, for the Southern African region, and then David Mongi for the Eastern African region. Thank you very much for attending today's webinar.